Now in this problem you're given a chessboard of size 8 by 8 and you start at any start position. We will be starting at 0, 0. And the problem is asking you to traverse the chessboard only through the moves of a knight until you've covered every spot in the 2D array without going over the same spot twice. From here it can go to 21 or it can go to 49, but it can also go up here and it can also go up here as well. We'll begin with this template. We have our knight's tour function, which is a Boolean function since we're only looking for one solution. We have our column and our row. We have the current index of the problem. And we have our chessboard here. We have the size of the chessboard. And we have the current move value. So on our first move, we have it labeled as 1. On our second move, we have it labeled as 2, and so on. That's what that means. And we have a can move knight's tour function. And this line here makes sure that the current spot in the 2D array isn't already taken, because the 2D array will be initialized to 0 values by default. So the first thing we wanted to do was we want to check whether we can make a move. So immediately we want to check if we cannot make a move in this spot, where we pass in our column, our row, our board, and the size of the board. If we cannot make this move, then we want to return false. So when we pass this, we know that the move is valid. So immediately what we can do is we can input the value. And when we make a move, we also want to increment the value. So it will be n++. Now once we made a move, we want to check straight afterwards how we solved the problem. So how do we know whether we've solved this problem? Well, if our index value is equal to the number of cells in the 2D array, that means we've covered every single spot. So what we want to do is we want to check whether index is equal to n times n minus 1. It's minus 1 because it's 0th index. If it is, then we want to return true. So if we pass this if statement, that means we haven't solved the problem, which means we want to recursively find more problems. So we want to recall knight's tour. We want to pass in our column, our row, our index plus 1, our array again, the size of the array, and then n. Also note that this is a Boolean function, so we want to pass this into an if statement. And if this call here returns true, and we also want to return true, because this implies the current state change returned a valid solution. Now, we have a problem here. The problem is that a knight can move in 8 different ways, and we've only covered one way. The first case is that a knight can go along to the right by 2 and then go down by 1. So that's one case filled in, and so what we'll have to do is we'll have to copy this 7 times. Now a knight can move 1 to the right and it can go 2 down. And now it could go 1 to the left and then 2 down. Or it can go 2 to the left and then 1 down, and then 2 to the right and then 1 up. Okay, so if we pass all of these if statements without returning true, that means that none of the moves produced a correct solution. And so if none of them produced a correct solution, that means this state change over here is invalid, as it does not give any solutions. So what we have to do is we need to undo it. And it's this line here that is the actual backtracking part. Also we did n++, which means we need to do n minus minus over here. And this is a Boolean function, so we still need to return something. So we can return false over here. And there we go. So yep. So the next problem is solving a maze, and this is very simple. Essentially we just have a start position and an end position, and we just want to find any path from the beginning to the end. And we don't have to find an optimal path, we're just looking for the first path we can find. And we have our maze in a 2D array, which is this maze over here. So the 1s are all the positions that we can move along, and the 0s are all the blocked positions. So what you'll find is a lot of these backtracking algorithms are very similar. So we can take this and we can actually just paste it in here, and we're passing in the maze, our solution, the column and the row, and then we're also passing in the size as well. So the way we check whether the problem is solved is we check whether the column number is equal to n-1 and the row number is equal to n-1. And n-1, n-1 is the last index of our 2D array, and we're going from 0, 0 to n-1, and that's why we check this. Now we want to change all instances of night store with find path, and we're passing in our maze, our solution. Now for the column and row numbers, what we have to remember is in the previous problem a knight had 8 different moves, but in this case in a maze you can either go up, down, left or right. So we only have 4 moves to think about, so we can remove the rest. Just quickly, I noticed that the C and the R's were flipped around. This is actually going to the right. This is going down. This is going left. And this is going up. Even though that the column and rows are flipped, the logic still works here if you just read it out. When we run this, we get an output of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the last problem is the n queens problem. And in this problem you're asked to find the total number of ways that you can place n queens on an n by n chessboard. And notice how the queens have to be placed in a valid position, meaning that they don't collide or interfere with each other. So for the 8 queens problem, we should have 92 solutions. The way this works is we will recursively move on to each row on the chessboard, starting at the beginning. So for example, we could place a queen here, and now we move on to the next row. We can't place a queen here, we can't place one here, and we move on to the next row. We can't place one here, but we can place one here. And we can also place one here. So what I'm doing here is I'm checking, is there a queen vertically above me, or along the same column, or on the same diagonal slope. Now you'll find in this case, I can't place a queen on any of these positions. So this recursive call here does not have a solution. So we must backtrack, and that means going a row above to the previous recursive call. So that means this state change here did not provide a correct solution on the next recursive call. So we need to undo this, so set it back to what it was before, and now we can try on the next column. So we can't place one here, and we can't place one here or here, but we can place one here. And then we just keep on repeating that process again and again until we complete the whole chessboard. And the next column here, which is the column after the 8th column, I mean the row, when we reach the 9th row, which means we've traversed over every single row on the chessboard, that means we found a solution. And if we found a solution, then we increment this to the next number. So because we're finding the total number of solutions, it's better to write this algorithm as a void function rather than a Boolean function. Okay, so I just quickly filled in the valid function. Note that on a chessboard, for the n queens problem, this queen does not need to check any of the rows below it because we are traversing the array in a top to bottom manner. And the queen doesn't need to check any of the columns on this row, since you can't have two queens on the same row. So all we're doing is we're checking the rows vertically above it, and we're checking all the diagonal slopes, so the negative and the positive diagonal slope. This here is checking the negative slope, and this is checking the positive slope. So when do we know when the problem is solved? Well, we said it was solved when the row number surpasses the number of rows. So if the row number is equal to n, right, because you have n minus 1 rows, so n would be the row after the n minus 1th row. So if row equals n, we can increment n, and we can exit. So if we get past this if statement, that means we have not found a solution. So we need to now look for a solution. We want to iterate through all of the columns on the current row. So if valid n queens, so we pass in our row, and we pass in our I for the current column number. And then we pass our baud, and then the n value. So if this placement is valid, then we can make the placement. So in baud row I, we can set this equal to 1. Now we want to move on to the next row and look for more solutions. So we call nq with our row, well, we move on to the next row. We pass in our n, our baud, and n. But we don't need to check whether this found a solution or not. Since we're trying to look for all solutions, we don't need to exit out of the function from here. So whether we find a solution or not, we want to still look for more solutions, so we still want to backtrack. So we set this back to 0. Right, so the main difference that we see here is if we're looking for only one solution or any solution, we typically use a Boolean function and we would return true after making our recursive call here to exit out of the loop. But if we're looking for the total number of solutions, or we're looking for a certain number of solutions, then we don't want to exit the function from here, we just want to backtrack immediately after our recursive call. So now we can see that we get the value 92. Okay, so now there's an optional extra challenge that you don't have to do, but I would recommend giving it a go. So this is called combination sum, and essentially you're given an array of values. So you could get this, and you have a sum value, which is 8, and you're supposed to find a combination of numbers from this array that will sum to 8. Now this could just be a simple sliding window question, but the catch here is that you can use the same number multiple times. So a valid solution to this problem could be 2, 2, 2, 2. So that could be a valid solution. And so this is very similar to another problem called the coin change problem, except that's a dynamic programming problem which focuses on finding an optimal solution. In this case, I want you to use backtracking to find all solutions to the problem. And so that is backtracking algorithms. Backtracking can get really complicated, and you could also write them iteratively as well. But generally you will be writing them recursively most of the time.